Hello, my name is Juan Mendez and this is my thesis defense. The title of this work is the use of deep reinforcement learning algorithms to aid in the solution of mechanical engineering problems. This is the agenda for the presentation. Unfortunately, we're not going to go into a lot of excruciating detail about the investigation because the time is limited. Before we start, I want to share with you the motivation behind this research using these two pictures. As we can see, the job of a mechanical engineer hasn't really changed much in the past century. We are still designing solutions. The thing that is changing is the technologies that we use or that we have on our disposal to solve those problems. In this video, we're going to talk about one of the most exciting fields of AI, and that is reinforcement learning. RL is a technique that is capable of solving optimization problems and is an essential toolset for the modern engineer. In this work, we are going to discuss how to take a classical mechanical engineering problem and transform it into a reinforcement learning problem. As we can see for the diagram, one of the main leading technologies that is shaping the world right now is AI in the fourth industrial revolution. These are the objectives of the investigation. Feel free to browse to read them properly. Now we begin with the section on why reinforcement learning is important for mechanical engineers. To answer this question, we first need to take a quick overview about the current state of AI. Here we can see the increase of hiring in AI professionals across the years. Now, in this graph, we can see the increase in private investment in AI. And finally, on this graph, we have the number of AI publications by field, where the most popular ones are pattern recognition and machine learning. What this graph tells us about is that the demand of professionals capable of using AI solutions is increasing exponentially. Now we move on one of the biggest reasons on why mechanical engineers should learn RL, and that is that classical approaches of solving control systems are getting more and more complex with the evolution of technology, up to the point that they are one of the hardest problems to solve. The fourth reason is that reinforcement learning has the ability to surpass human beings in solving complex problems. The fifth reason is that we need to increase the amount of research done in mechanical engineering using reinforcement learning applications. And the final reason is that it is now both affordable and accessible to implement this technique using free software such as TensorFlow and Google Colab. Now that we know the importance of reinforcement learning in mechanical engineering, it's time to learn about the basics of reinforcement learning. Reinforcement learning is a framework for learning how to solve sequential decision-making problems by maximizing the reward signal output by an environment. The way it learns the base course of action is by exploring the environment and receiving feedback on how good or how bad the actions that they took were. In this slide, we can see the different fields that RL is based on, and how this discipline tries to imitate the process of how living things learn. Here we have the basic framework for a reinforcement learning problem, where the environment outputs a state reward pair and the agent responds with an action. These are the type of environments that one might encounter. It's important that we learn how to categorize them because it decides which RL algorithms can solve the problem. Now, the way we need to formulate the optimization problem is by converting it into a Markov decision process. Here we have the sub-elements of a reinforcement learning system. Finally, before we move on with the RL algorithms, we need to know how they are separated. These are the three main types of RL algorithms, being model-based, value-based, and policy-based. Now we move on with deep reinforcement learning algorithms. But first, here is a diagram of the subsets of artificial intelligence. As we can see, deep reinforcement learning is the intersection between two major fields, being deep learning and reinforcement learning. Now, the main reason on why we use deep RL algorithms instead of classical RL is that it's just too expensive for classical approaches in both memory and processing power. Moving on, we have that deep reinforcement learning is simply the use of reinforcement learning algorithms with the help of networks that works as approximators to a certain mappings of some states. Because time of constraints, we're going to take a quick glance about the deep reinforcement learning algorithms. Feel free to pause at any time in order to understand the basics of them. Now, DQN uses the Bellman optimal equation in order to create a loss function that the agent needs to optimize in order to the network learn. DQN uses some intelligent tricks such as epsilon greedy policies, targeted networks, and experience replays to stabilize the learning process. Here's a diagram of a DQN architecture. The other three methods that we are going to review are based on policy grading methods. The objective of a PG method is to find a gradient of the objective function in order to slowly actualize the network parameters. Advantage actor critic methods uses the advantage to take a specific action at a given state in order to optimize the network parameters to learn the policy. One of the clever tricks that it uses is that it uses a dual network system and also uses an stochastic policy to explore the environment. Here's a diagram of the architecture of the A to C algorithm. And finally, we have one of the most important aspects of actor advantage networks, and is that it can learn in parallel with multiple agents at once. Moving on with deep deterministic policy networks, is that the DPG uses a deterministic policy in order to learn the Q function of the environment. It uses similar tricks such as target networks and replay buffers. It also uses soft actualizations and the noise function to explore the environment. Here's the architecture of the DPG. And for the final algorithm, we have proximal policy optimization. This algorithm is based on the principle of network gradients. It's an improvement over an existing algorithms that is trust region policy optimization. The idea behind it is to change the policy gradually within a region that we know that won't break the learning process. Here we have the algorithm and a graph of the function alclip, that is the one that is in charge with constraining the changing in parameters of the network. Here is a table of the use cases of each of the algorithms. In this diagram, we are comparing the algorithms against one another, the advantages and the disadvantages that they have, the three main drivers of the choosing of an algorithm is the sample efficiency of the algorithm, the versatility, and the computational simplicity of running the algorithm. Now we finally move to the translation process. Here's the methodology that I create to convert a mechanical problem into an RL problem. It consists of 5 steps: recognize the type of environment, then create the environment, then design the state signal function, afterwards design the reward signal, and finally select the reinforcement algorithm. Unfortunately, sometimes this process is not as linear as we want it to be, so I create a flow diagram to understand how to take decisions when the problem fails. Here's the first part of the flow diagram, where there are many questions that might lead to the environment to be modified in order to work properly. In the second part of the diagram, if all goes well, we only have to do high pair parameter tuning in order to maximize the agent learning rate. So, in order to test the different algorithms and the methodology that was created, I developed an open software called Engine, which you can play with. Engine enables the engineer to create their own custom RL problems and solving them using the pool of algorithms that we describe on this investigation. They can also create their own reinforcement learning algorithms, and the invitation is to use the software and create a pool of algorithms in order to mechanical engineers explore the benefits that might have this type of technique. Now we move on with the practical implementation of mechanical engineering problems. The first problem is how to optimize the weight of a bar. This is the MDP formulation For the problem, as we can see, we decide to use continuous set of actions in order to decide the radii of the bars. In this graph, we are comparing the learning process of a A2C agent against a PPO agent. We can see that the A2C learned a lot faster the policy of the environment. And here's a comparison between a classical approach versus a reinforcement learning approach. The second environment is a self-balancing robot that its objective is to stay upright the most time possible. Here's the table of the MDP formulation for the balancing robot. Here is a comparison between the two graphs of A2C and PPO. So, in order to solve the problem, I used a physical engine called PyBullet that enables me to create the robot. Here is the first 100 episodes and then the training process after 500,000 episodes. Now we move on with the third practical case, and that is a fixed cantilever beam that we also need to optimize the weight of it. The MDP formulation is quite similar to the first environment, so we are not going to include it. And here is a graph with the learning process of both A2C and DDPG in this algorithm. And finally, here's a comparison between the solution made by classical approach versus the reinforcement learning solution. These are the main challenges that reinforcement learning needs to overcome. The first one being exploration versus exploitation, up to what point we explore the environment. The second one being the training stability, how we stabilize the training process. The third one being probably one of the hardest, and is how we should reward the agent. The fourth one being the gap between the simulated environment and the real thing. And lastly, the AI safety and ethics of these types of solutions. Now, for future work, one of the things that we might like to see is narrowing the sim to real life. Finally, for concluding this video, we have that due to the versatility of reinforcement learning, almost any mechanical engineering problem can be modeled as a reinforcement learning problem. We also have that this is one of the most promising fields in artificial intelligence for mechanical engineers, and there is a lot of research and applications to be explored of this type of technique. Thank you for watching the video.